This research paper introduces a Python-based computer program for analyzing the performance of superheated steam power cycles using the open-source thermodynamic library Cantera. The study aims to fill a gap in the existing Cantera examples by providing a solver for superheated steam cycles, which can be applied to both subcritical and supercritical types of superheating. The developed code is an extension of the saturated cycle solver provided by Cantera, allowing users to input up to 5 parameters to determine the corresponding superheated cycle and receive a summary of the predicted performance. The code is written in Python, a popular language used in data science and machine learning, and requires a Cantera version 2.5.0 or later. The latest version of Cantera, 2.6.0, was used in this study. The code content is provided in the appendices, with comments explaining each portion of the code. The superheated steam cycle has 2 advantages over the saturated steam cycle: increased energy conversion efficiency and prevention of excessive liquid water droplet formation inside the steam turbine, which can cause damage. The developed code utilizes built-in thermodynamic properties for water in Cantera and can be applied to both subcritical and supercritical steam cycles. A validation case was conducted using a benchmarking superheated steam cycle whose solution is available in the literature, demonstrating the accuracy of the proposed solver. The study also highlights the ability of the proposed code to model both subcritical and supercritical steam cycles, as well as changes made to the original Cantera built-in computer code that led to the proposed code. In conclusion, the developed Python-based computer program provides a valuable tool for modeling the performance of superheated steam power cycles, enhancing the efficiency and reliability of electricity generation. The code is free to access, does not require many inputs from the user, and gives results in a very short time. The paper presents a Python code for simulating the thermodynamic cycle of a steam power plant, focusing on the role of water as the working fluid. It begins with an introductory section that outlines the purpose of the code and the required version of the Cantera library. The code then defines 3 functions: compress, expand, and print state. The compress function models the adiabatic compression process in a water pump, computing the amount of work energy needed per kilogram of water during this process. The expand function models the adiabatic expansion process in a turbine, computing the amount of work energy extracted from the steam during the expansion. The print state function displays a formatted summary about each water state, including temperature, pressure, specific enthalpy, and specific entropy relative to the reference triple point state of pure liquid water. The main part of the code starts by establishing a water species object and defining reference-specific enthalpy and entropy at the triple point of liquid water. The code then sets the water conditions for each state in the steam cycle, from state 1 to state 4, simulating the compression, heat addition, expansion, and heat rejection processes. For each state, the absolute specific enthalpy is obtained from the water object and used to compute the amount of work energy or heat energy involved in the corresponding process. A summary of each state is displayed on the screen using the print state function. The code computes the overall efficiency of the cycle and the amount of heat energy rejected per kilogram of water during the heat rejection process. The paper provides a detailed explanation of the code's structure and function definitions, as well as the input parameters and their meanings. It also discusses the limitations and assumptions of the model, such as neglecting heat transfer and losses during the compression and expansion processes. The paper presents a novel Python-based computer solver for analyzing and optimizing the thermodynamic performance of superheated steam power cycles, which are more efficient than traditional saturated steam cycles but require sophisticated materials. This solver is an extension of the original Cantera example code, Rankine.py, for saturated steam cycles, allowing users to select target temperatures and pressures for superheated steam and condensation. It also provides a more user-friendly and concise state summary, including steam quality in liquid-vapor mixtures, and a detailed cycle performance summary at the end. The solver code is validated through a benchmarking case, where it closely matches the results from an external study, demonstrating its validity. The code simulates the entire steam power cycle, starting with the initial state 1, then proceeding to states 2, 3, and 4, simulating the pump, boiler, turbine, and condenser processes. The overall cycle efficiency is computed by subtracting the pump work from the turbine work and dividing this net output work by the heat added in the boiler. The results of the benchmarking case are presented in Table IV, showing a cycle efficiency of 38.60%, which is very close to the value obtained in the reference study. The code's flexibility allows for both subcritical and supercritical steam cycles, with the benchmarking case being a subcritical type due to its maximum absolute pressure being below the critical pressure of water. Supercritical cycles tend to provide higher energy conversion efficiency but require more sophisticated materials. The solver's modifications include the ability to select target temperatures and pressures, a revised state summary, and a detailed cycle performance summary. This paper presents a Python-based solver for analyzing arbitrary steam power cycles with superheating, applicable to both subcritical and supercritical types. The solver is an extension of the Cantera software package, version 2.5.0 or later, and includes 87 lines of code. It demonstrates the power of computer-based analysis and engineering modeling, providing a nearly instantaneous and precise thermodynamic cycle analysis. The solver can be beneficial for engineers, researchers, or students involved in various fields such as fuel-fired steam power plants, combined cycle power plants, nuclear power plants, solar thermal power plants, thermodynamics, computational modeling, or Python programming. The paper discusses the importance of thermodynamic and transport property modeling in supercritical water, as well as the use of organic Rankine cycle systems. It also highlights the significance of the critical point in phase changes and its relevance to the operation of steam power plants. Moreover, it emphasizes the role of computer solvers in optimizing the performance of steam turbines and reducing energy consumption. The study references several key research papers and resources, including a detailed analysis of the thermodynamics of lithium-ion battery intercalation materials using the open-source software Cantera, and the use of a genetic algorithm for thermal design and optimization of a heat recovery steam generator in a combined cycle power plant. The paper also mentions the importance of validating the developed code and its documentation, which constitutes the main contribution of this study. The solver code is provided in the appendices, with an example output showing the analysis results. The paper also includes a comprehensive list of references, covering various aspects of thermodynamics, computational modeling, and Python programming. The paper presents a comprehensive analysis of a thermodynamic cycle for water, focusing on the efficiency and performance of various processes such as compression, heating, and expansion. It begins by defining key parameters including maximum and minimum pressures, maximum temperature, and the isentropic efficiency for both pumps and turbines. The main analysis starts with the creation of an object representing water using the CoolProp library. The reference state is set to the triple point of water, which is a saturated liquid state. The initial state is then defined as saturated liquid water at the minimum pressure, P_min. The first process involves adiabatically compressing the water to the maximum pressure, P_max, using a pump with an isentropic efficiency of eta_pump. This results in a change in enthalpy, which represents the work done during this process. Next, heat is added to the water at a constant pressure until it reaches the desired superheated steam state, with the maximum temperature, T_max. The heat added is calculated as the difference in enthalpy between the initial and final states of this process. Following this, the water undergoes an adiabatic expansion back to the initial pressure, P1, using a turbine with an isentropic efficiency of eta_turbine. The work generated during this process is also calculated as the difference in enthalpy between the initial and final states. The efficiency of the entire cycle is then determined by dividing the net output work, turbine work minus pump work, by the input heat. The paper also calculates and prints out various other relevant parameters, including the net output work, input heat, heat rejected, and cycle efficiency. The provided Python code demonstrates how to implement these processes using the CoolProp library, allowing for precise calculations of thermodynamic properties and efficiency. This analysis provides valuable insights into the design and optimization of thermodynamic cycles, highlighting the importance of considering both the isentropic efficiency of components and the thermodynamic properties of the working fluid. Here is the combined summary of pages 11 and 12. The provided appendix presents a sample output of the program code, which calculates the thermodynamic properties of a system across 4 distinct states. State 1 and State 4 exhibit similar temperature and pressure conditions, with specific enthalpy and entropy values of 210.5134 kJ per kilogram and 0.707436 kJ per kilogram K, and 2329.4947 kJ per kilogram and 7.258869 kJ per kilogram K, respectively. Notably, State 4 is characterized as a liquid-gas mixture with a quality of 0.889556. In contrast, State 2 and State 3 demonstrate drastically different conditions, with State 2 featuring a temperature of 50.47 degrees Celsius, absolute pressure of 50.000 bars, and specific enthalpy and entropy values of 215.5568 kJ per kilogram and 0.707436 kJ per kilogram K, respectively. State 3, on the other hand, exhibits a temperature of 600.00 degrees Celsius, absolute pressure of 50.000 bars, and specific enthalpy and entropy values of 3666.4839 kJ per kilogram and 7.258869 kJ per kilogram K, respectively. The cycle analysis reveals an input pump work per kilogram of 5.04 kJ per kilogram, output turbine work per kilogram of 1336.99 kJ per kilogram, and a net output work per kilogram of 1331.95 kJ per kilogram. Furthermore, the input heat per kilogram is calculated to be 3450.93 kJ per kilogram, with a heat rejection per kilogram of 2118.98 kJ per kilogram. The cycle efficiency is determined to be 38.60%. These results underscore the significance of accurately modeling thermodynamic systems to optimize performance and efficiency.